Hi, welcome back, learners. In this video on the topic probability, which is actually a CAPS Mathematics Grade 12 topic, we're going to look at the fundamental counting principle. This is part one of part two. In this part, we're going to introduce the fundamental counting principle and then do some problems on arrangement of objects and some seating arrangements. Probability, Fundamental Counting Principle, Part 1, Introduction of the Counting Principle and Arrangement of Objects and some seating arrangements. Let's continue. Let's look at the outcomes of the videos on probability. There's a Part 1, and in Part 1 we will look at the factorial notation and then the concept of counting principle, fundamental counting principle. Then there'll be two types of applications that we're going to look at. The one is arrangement of objects in general, and then specifically also some seating arrangements. There'll also be at the end an exercise worksheet. And then in part two, the other video, there we're going to look at counting how committees can be elected, and then we're also going to look at passwords, PIN codes, and numbers, and then we're going to look at some problems involving probability, and all my videos always end with a exercise worksheet, right? So there's part one and part two. Firstly, let's look at the factorial notation. Let's go over some no notations. There we have multiplication by n, and there we have raising something to the power n. That is multiplication, and there we have power there. So as an example, we have 8 times n, and the other one we have 8 raised to the exponent n. 8 times n, that means a plus a plus a plus a4 in terms of a. Let's look at the other one. A times a times a times a4 in factors of a. So in this case there we have a repeated addition. Every time we add, and the other one there we have repeated multiplication. We multiply by a and multiply by a, so that's repeated. So we can see this year for repeated we have a short way of writing repeated addition. For repeated multiplication we have a short way of doing that. For example, 5 times 4, that's a short way of saying 5 plus 5 plus 5 plus 5, right? So the 5 is added 4 times. Similarly, 5 to the 4, that's 5 times 5 times 5 times 5. So there we've got the abbreviated form of that. Now let's introduce another notation. See there we've got an exclamation mark, and that we actually refer to as a factorial. Right? For example, n factorial, what does that mean? We could have 7 factorial, 11 factorial. N has to be a natural number. So that actually means it's the product of the descending natural numbers from n to 1. Right? So if I have n, descending means it becomes 1 less, n minus 1, then n minus 2, and then n minus 3, etc. Then until we get 3 times 2 times 1, because it goes up to 1. Okay? We can also write that as n times n minus 1 factorial. There's the n, and this part here is actually n minus 1 factorial. For example, I've got 5 factorial, so we start with 5, then descending, it's 4 times 3 times 2 until we get to 1, right? That could also be written as 5, and you see this 4 times 3 times 2 times 1 is actually 4 factorial. Similarly, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which can also be written as 8 times 7 factorial. So you see this descending product is actually quite a long. Just imagine I have 20 times 19, it takes, and that's still a small number. What if I have 100? So this factorial is just an abbreviate way. The same way if I had 6 times 6 times 6 times 6, I can write that as 6 to the 4, short way. Or if I had 7 plus 7 plus 7 plus 7 plus 7. I can just write it as 7 times 5. So like the repeated multiplication or repeated addition, 8, this factorial is just a abbreviated way of writing a product of descending natural numbers up to the number 1. In the next slide, we're actually going to show you some calculations involving factorials. So let's look at some calculations involving factorial. So we have n factorial is n times n minus 1. You see it's decreasing until we end up with times 1. Also, it can be written as n factorial times n minus 1 factorial. But what about 0 factorial? Let's just see whether that is possible. So 5 factorial, it's 5 times 4 factorial, and that 4 factorial can be written as 5 minus 1 there, right? Similarly, 4 factorial, that's 4 times 3 factorial, and 3, you know, is the same as 4 minus 1. You see a pattern here? The next one, I have 3 factorial is 3 times 2 factorial, and 2 is actually 3 minus 1 factorial, right? The next one, there you can see 2, so there we have a pattern, 5 minus 1, 4 minus 1, 3 minus 1, 2 minus 1. So what will the next one be? 1 factorial, okay? So there I have 2 minus 1, I have 1 minus 1. But you just look at this here, 4, 3, 2, 1, and the next number would be 0 factorial. Now if we look at this, 1 factorial is 1. And 1 times 0 factorial is just 0. 1 times, that's identity. 1 times 0 factorial is 0 factorial. So there we have that 0 factorial is 1. We'll just also show it to you on the calculator as well. So if you use your scientific calculator, you'll see there's a key here with the x, the one that you use for reciprocals, and there's the x factorial key there. So we have to enter your number, but you can see that is in yellow, so you have to use the shift key. So you the number, you enter it, then shift, and then if you enter that key there, you'll get the value there. For example, I enter 5, shift 5, then shift that, and I can get the value for 5 factorial. Now, we just like you to try these few examples. So maybe pause the video and then try that and give you some chance. It should be able to do that quickly in, let's say, 2 minutes, and then you can start again. So let's try it on your own first. Just pause the video, and then we can continue. Let's continue. Let's see, what did you get for 8 factorial? That's correct, 40,320. 5 factorial, that's correct, 2,880. Very good. That one, this is the type of calculation that we need, right? So, and there's 3,360. So we'll have one, we have to just work out the factorial, maybe a product of factorials, or maybe you have sometimes a quotient involved there, okay? So that's the type of calculation that you know, and you can just use your calculator there. Or sometimes, let's say let's try if you maybe take 10 factorial, see it's quite a large number here. So let's go to the next slide. Now that we sorted out our notation, we're ready to look at the fundamental counting principle, right? Fundamental, we can also refer to that as the basic counting principle. Now, when more than one event occurs, more than one event we also refer to as a compound event. So when we have more than one event occurring, it will be important for us to be able to quickly determine the total number of outcomes for the compound event. That is, we actually want to determine the size of the sample space, and that is our whole objective here. Now let's see how we can count the number of outcomes of a compound event. How many outcomes are possible? To be able to do this, we have two options. We can either make use of a tree diagram, or we can actually list all the outcomes. And we're going to try both in the next few examples, and then we'll be able to deduce a rule. So our goal is actually to determine the number of possible outcomes. In other words, we want to determine how many outcomes are there, and we don't actually want to find the actual outcomes, right? So we have to find a technique of counting the number of outcomes without actually listing all the outcomes. So the procedure we're going to follow would be as follows. Firstly, we're going to list all the outcomes, or we're going to use a tree diagram. And after doing that, we'll be able to count the actual number of outcomes. And then lastly, from that counting, we were able to generalize and to derive a simple calculation rule for determining the total number of outcomes. Now let us consider an example how we can determine the total number of outcomes of compound events using tree diagrams and listing the outcomes. Let's consider two events. The first event, a coin is tossed, right? That means it can toss there. It can either be, that's correct, can be heads or tails. And then we have a die that is rolled. There we have a die rolling. But it's important here that both the coin and the die need to be fair. In other words, it needs to be unbiased coin and unbiased die. So let's see now. Let's start with the tree diagram. So if we toss a coin, it can either be heads or it can be tails. So the outcomes that I can have there for tossing a coin would then be, the number of outcomes would be 2. Okay? Now, if I have heads and I now roll a die, it can be, I can have the option of heads and 1 and heads and 2 and heads and 3, heads and 4, heads and 5, heads and 6, right? So in other words, rolling a die, the number of outcomes of rolling the die would be, there are 6 possible outcomes. Okay? In the same way, we can then actually list the outcomes, which is heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, and we see there the outcomes there would be 6. Now, similarly, with a tail, I can have exactly the same options. I can have a tail with 1, a tail with 2, 3, 4, 5, and 6. Now, if we count the number of outcomes, we can see there we have 6, and there we have 6. And 6 and 6 gives me a total of 12 outcomes. But if we look at those 12 outcomes, we can actually see that that 12 is actually the product of the 2 and the 6, right? So this already gives us some idea how we can obtain the number of outcomes for a compound event. Let's look at another example now. Now let's consider a second example. Again, we have 2 events. In this case, the one event is spinning a spinner. So there we have a spinner, and that's spinning it. And then we have also tossing a die, rolling a die. And there we have a die, and that die is being rolled. Now, let's use a tree diagram again here. So first of all, with tossing a spinner, spinning a spinner, we have a possibility of a 1, and we have a possibility of a 2, and we have a possibility of a 3, and a 4, and a 5, right? So the number of outcomes of spinning there would be 5, right? Now, if you go to the 1 now again here, we see that if I have a 1 and I now roll the die, I can have either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So I can have 1 1 and 1 2 and 1 3 and 1 4. So the number of outcomes of rolling a die in this case is 6. And similarly, I can do find exactly the same outcomes associated with 2, and then with 3, and then with 4, and then with 5, right? So now we want to find the total number of outcomes. If I now look at the total outcomes of spinning and rolling a die, if we now count this, we can see there we have 6, and then another 6, which is 12, and another 6, which is 18, and then 24 and 30. So the total number of outcomes here is 30, right? You can already see listing this would be, very time consuming, right? Even doing the tree diagram has already been time consuming there. What about listing? It's even more. So, but looking at the 30, we can see there's actually a way we could have obtained that 30. That's right. It's actually the product of the 5 and the 6, right? Now we will use these two examples to come up to generalize and find a way in which we can find the total number of outcomes without actually setting up a tree diagram or listing the outcomes there. Let's look at the next slide. Now, from these two examples, we've seen that we can use tree diagrams and we can list the outcomes, but doing that is actually very time consuming, especially if we're going to even use larger. There we only use 2 events. What if we have 3 or 4 events? The tree diagrams can become very time consuming and very difficult actually to draw. But from these examples, we notice that we can find the total number of outcomes by doing a simple calculation. And what was that calculation? Yes, we'll have to just find the product of the number of outcomes for each event. Now let's just go to the next slide and just show that to you in a little. Now we can actually deduce a rule that we can use there. If an event can be done in m ways, let's say the one event can be done in m ways, right? And then a second event can be done in n ways, and then we have a third event or task that can be done in k ways. Now to find the total number of possible outcomes for these 3 tasks, we just find the product of the 3. So I have to find the product of the m, the n, and the k. That means there we have it, m times n times k. And because we use product, this rule is also sometimes known as the rule of product or the product rule. So it's just m times n times k. If there's a fourth one, it will be just times the other one. And that is our fundamental counting principle. Now it's important for you to note the following about the fundamental rule counting principle. That this counting principle or this rule only applies when all the choices are independent of each other. What do we mean by independent of each other? That the one choice does not depend on another choice. Also, that the compound events therefore must occur one after each other. They cannot occur the same time. Now let's look at some examples where we can apply the fundamental counting principle. But here, you're going to be given a chance to do it on your own. So let's see what we have here. A coin is tossed, and a spinner is spinned, and a die is rolled, right? And here we have to determine the total number of outcomes of the 3 events. Now, I suggest you pause the video, do the solution, and I think 1 minute should be more than enough. So, and then you come back again, right? And you start the video again. So let's pause there. Now let's look at your solutions. We have a coin, and then we have a spinner, and then we have a die. For the coin, we have 2 options. That's correct. And for the spinner, we have 5 options. And for the die, we have 6. These events are independent, and we can apply the fundamental counting rule or the product rule. So we find the product, right? So therefore, the total number of outcomes of these 3 events is 2 times 5 times 6, and you don't even need a calculator to do that, and that is 60. So we're going to look at another one for you to try as well. Now let's look at another one for you to apply the fundamental counting principle. A new car is available in different body styles. There we have body styles and different transmissions and engine capacity and exterior and interior colors, and all of this here is tabulated here. So we can see there we have body styles. You can see there's 5 cabriolet, there's a cabriolet, there's the station wagon and the hatchback and the sedan, etc. Right? So we want to determine the total number of options or choices available based on this information here. So we have to find the solution. I suggest you pause the video, and maybe to help you, the previous one was 1 minute. Let's do it a little bit better. Let's give you a lot of time. You have 90 seconds in which to do this, right? Pause the video and then we'll come back again. Okay, let's see what we've done here. So we have the body style, it's 5 options, and then the transmission, that we have 2, and for the engine we have 3, and for the exterior colors you can count there 1, 2, 3, 4, 5, 6, and for the interior colors we have 4. These are independent events, so we can apply the product rule. So you find the product of 5 times 2 times 3 times 6 times 4. So the total number of options here is 5 times 2 times 3 times 6 times 4. Maybe you need a calculator, but it's also possible to do it without 7. And there we have a total of 720. Just look at this here. 720. Just imagine if we had to set up a tree diagram for this. First of all, we'll have 5 branches. Then it branches out in another 2. And then in another 3. Then in another 6. And it's going to be very time consuming. Actually very difficult to do a nice neat setup there. So using the product rule or the fundamental counting principle simplifies the counting a lot here. Let's continue now. There's another rule we want to look at. Let's consider the following examples. A class consists of 15 boys and 18 girls. So there's some of the boys and the girls. The teacher would like to choose one of the learners, one, to act as a class monitor. How many ways can the teacher choose one learner? So let's see now. What do we want to do? What needs to be done? He has to make a choice, right? He has to choose a boy. When you choose, it's this or the other. So for choice, you have a or. For the boys, we've got 15 choices, and for the girl, we have 18 choices, right? So the total choices there would be 15 plus 18, and that is 33. So we add. So you choose between one or the other, we will add. Let's take a second example. We've got a vending machine that has the following items for sale. Right, we've got 5 chocolate bars, there's the chocolate bars, and then we have snack packs, there's the snack packs, 6 types of juices there. And how many ways can you choose one of the items? Emphasis on, you want to choose one. So let's see what we need to do. We need to choose. You can either choose a choc bar, or you can choose a snack pack, or you can choose that, right? Now, choc bar, how many choices do we have? 5. Snack pack, we have 4. And for fruit juice, we have 6. So our total choices there would be 5 plus 4 plus 6. That means we add the choices there. We've got a total of 15 choices there. Now let's get a rule for this. Let's just look at our rule here. If 3 events can be done in m ways, n ways, or k ways, then the number of choices to do one of these events is the sum m plus n plus k. So in the rule of sum, we have event E1. We choose between event E1 or E2 or E3. Then we have to add the number of choices, right? If you have to choose one of these events. And rule of product would be that you have event E1 and event E2 and event E3, then we multiply the number of choices here. So in the case of sum, we have or, then we have or, then we'll add. If we have and here, then we multiply our choices. Remember the product rule, we emphasize that the choices have to be independent of each other. Now, what if we have choices that are not independent of each other? What if they're not independent? Let's consider an example and we can show you what needs to be done. Let's take example number 4 again, right? So there we have the information of number 4, but here we have something else here. The cabriolet version, in other words, this version here, is only available in that size and in automatic. You don't have it in the other. So we want to determine the total number of choices available now based on this. Now we can see the choices are no longer independent of each other. So it depends what you choose. If you choose a sedan, you've got some options. If you choose a cabriolet, your options are different, right? So now let's look at the solution of this example. Recall that the cabriolet version is only available as a 3500cc automatic. Say there's the data that we have. So let's look at the solution. Because the cabriolet is only available as a 3500cc automatic, it means we've got choices, and the choices there depend on the body style chosen. What are the choices? Either cabriolet or another style. Now let's choose a cabriolet. For the cabriolet, the body style, it's fixed, so that's just one, right? Transmission only comes in automatic, so no choice for the transmission. Engine capacity, only one choice there, right? And then exterior colors, we still have all 6 colors available. and then for the interior we'll all have 4. So here we're going to apply the product rule. Let's look at the other choice. For the other styles, we've got 4 styles to choose from. Then we still have the 2 transmission styles. Can have any of the 3 engine capacities, any 6 of the exterior colors, and any 4 of the interior. Again, we apply the product rule here. Now, because of cabriolet or, we're going to apply the sum. So the or indicates we're going to have the sum of those choices. So the total choices for the cabriolet, we have a total of 24. And for the other style, we have a total of 576. And then we find the sum of that. So the sum here would give you a total of 600 choices. Let's look at another example where choices are not independent. Here we have data about some sneaker options. And we have 3 brands. There's 3 brands, and there's just a sample to show you in case you don't know what a sneaker is. Now let's see here. The salesperson informs the customer that black Nike sneakers are out of stock. Now determine the number of choices now available if black Nike sneakers are out of stock. So let's see. This here would imply that the choices are now dependent on the brand. And what are the brands? You either have a Nike or you have another brand. So if we have Nike, because Nike is you only have 1 choice there, but you're choosing Nike. And then black, you only have you don't have black anymore, so you've got 4 other colors that you can choose from. And then for the uppers, we still have 3. And here we'll apply the product rule. So that's 1 times 4 times 3, which we can easily see that is 12. Let's look at the other choice. The other brand, there are 2 other brands, Adidas and Puma. And there's no restriction on colors, so we can have any of the 5 colors, and we can have any of the 4 uppers. Again, we apply the product rule, and 2 times 5 times 3, easy, that is 30. Because we're making a choice between Nike or the other brand, that implies that we're going to use the sum rule. So we're going to add the choices of Nike and the choices of the other brands there. So for Nike we said 12, and for the other brand there we have 30, and adding that together gives us a total of 42 there. Now we're going to look at counting arrangements of objects here. Right? And we'll have a number of examples, and we'll have some rules to assist you here as well. We'll look at one example, and then from these examples we'll be able to determine a general rule. Let's take this example here. In how many ways can all 5 books be arranged? So here we have 5 books, and we want to see in how many ways we can arrange them. So let's see what we can do here. There are 5 places for the books. So let's look at the first place. How many books do we have? We have 5, so any of the 5 can fit there. Second place, we've used up 1 of the books, so we only have 4 more books left. Now we only have 3 more books left. Then we have 2 more. And then lastly, I only have 1 more. We can apply the product rule here. And then we get the total number of choices. If we have different objects, it's going to be 5 times 4 times 3 times 2 times 1. Do you notice anything here? Remind you of anything? Yes, that is product of descending natural numbers, and that's correct, it's the factorial. So that's 5 factorial there, right? We can see there, even if I should now have had 10 books and I want to arrange all 10 books, it's going to just become 10 factorial. If I have 20 books, it's going to be 20 factorial if they are all of if the objects are all different. Now let's look at the second example. We're going to use those same books again, but here we don't want to arrange all the books. We want to arrange only 3 of the 5 books. So let's see how we can do that. So we just create our spaces there. So the first book, we have a place we can put any of the 5 books in there. And for the second space, we can put any of the remaining 4. And then for the third one, we can put down any of the remaining. 1 less than 4 is 3. So we can apply the product rule. So the number of arrangements there would be 5 times 4 times 3, and 5 times 4 times 3, very easy, that is equal to 60. Now let's look at that 5 times 4 times 3. You know, if we have a number and we multiply a number by 1, it still remains the same number, right? And there are many identities for 1. So if I take 5 times 4 times 3, if I multiply with 2 times 1, I also need to divide by 2 times 1. Otherwise, it won't be an identity that I'm applying there. Now, do you notice something about the numerator? Look at it again. That's correct. That is, I can write the short form of that. That's 5 factorial. And 2 times 1 is 2 factorial. But 2 is actually 5 minus 3. Right? So the 5 books minus the 3 down to 8, that is actually the 2. So you can also do that. Just do that in the calculator. And we see there we have 60. Right? So if I should have 10 books here, and I want to arrange 4 of them, it will be 10 factorial, and then 10 subtract 4, which will give me 6, and that will give me 6 factorial, right? So it will be, you can do exactly the same there. Just if you change the number, you can follow that particular pattern. Now, based on those 2 examples, we can then generalize. So we can see that if we have n different objects, important they must be different, they can be arranged in n factorial ways, right? For example, if I have 20 different objects and I want to arrange all 20 of them, they can be arranged in 20 factorial ways there. So then we had the other case there, we would want to arrange some of the different objects, like r of n. So that will be n factorial, and then we find the difference between them, and that will give us the number of different arrangements we'll get if we just want to arrange a certain number of the different objects there. Now let's apply these 2 rules we've just derived to the following example. Here we have some fruit, and we want to know in how many different ways can all the fruits be arranged, and then B, 4 of the fruits be arranged. So this is the one for you to try. So you can pause the video, and I'll be very generous. Let me give you 3 minutes in which to do that. So pause, and then we continue. So let's look at the solution now. First of all, what we have to do, we have to count how many items are given. So it's 1, 2, 3, 4, 5, 6, 7. There are 8 different fruits there. That's important. And in how many ways can we arrange 8? That's correct. We can arrange it in 8 factorial. And 8 factorial we can calculate. It's 40,320. See, quite a large number. Now, let's look at the second question. We want to arrange 4 of the fruits, right? So let's see first. So for the first fruit, we have a choice of 8. Then for the second fruit, we have a choice of 7, right? And then for the third one there, we have a choice of 6. And then next one, we have a choice of 5. So there are 8 times 7 times 6 times 5 there. So that gives us 1,680. You could also have done it using our rule there. We have 8 factorial, but we want to arrange only 4, so it's 8 factorial. Let's see there. 8 factorial divided by 8 subtract 4 factorial. Just do that in the calculator, and let's see. It's exactly the same. Now we're going to go a little bit further here. We want to arrange objects, but the objects are not all the same. There are some of them that are identical. And let's just take an example, and then from these examples we'll be able to generalize. I'm going to take 2 examples, and then we'll be able to see a short way of doing that. We want to determine how many distinct ways can the letters R, R, N be arranged. You notice something there already? That's correct. There's a repetition of the letter R. Okay. So if the 3 letters were different, if they were all different, then that would have been easy. And the answer is just 3 factorial. But now they are not different. This R and that R is the same. Now to help us distinguish between the two R's, we're going to write the one R like that, and let's just have a more cursor form of writing that, the other R there, right? A nice fancy handwriting R. So R, and that is R and R, but I'm just writing it in a different font there. So we're going to do that in the next slide, and we want to get a general rule, and we're going to arrange RRN. Okay, so there are three letters with different, as we said, that we're going to arrange them in 3 factorial ways, but they are not different. Let's actually look at those. 3 factorial ways are 6 arrangements. 3 times 2 times 1 is 6. Let's look at the first one. I can have a R and a R and an N, right? First 2 R's and then an N, but let's switch around those 2 R's. So that's the, right? And then we can have an R and an N followed by another R. Let's switch around those 2 R's. Okay, or we can start with an N. We can have an N and an R and an R, and let's switch around that. So if you look at that, there we see actually 6 arrangements. But remember, the 2 R's are not different. I just added cursive. They're identical. So in actual fact, this is exactly the same arrangement. So that's 1, 2, 3. So in fact, here we only have 3 different arrangements. So if we have a repetition, we actually have duplicate arrangements, identical arrangements there. So the number of different ways in this case is 3. Okay, but let's see what we can do with that 3. Again, the same way, using our identity of multiplying by 1. If I multiply the 3 with 2 times 1, and then I divide it by it, I haven't changed it. And what do you notice about 3 times 2 times 1? There, we can have a short way of writing that. That is 3 factorial. And 2 times 1 is 2 factorial, right? So we take the 3 factorial, and there are 2 R's, so we divide it by 2 factorial. Okay, let's say we had 10 letters, and there were 10 letters, but we have 3 R's, the identical R's, so that will be 10 factorial divided by 3 factorial there. Now let's take a second example, and then after this we'll be able to generalize. Here we have 11 files. We count there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 files, right? And they need to be arranged, right? All 11 need to be arranged. But it is obvious some of the files have the same color. They're duplicates, so they're identical. We have yellow. How many yellows? We have 2. Then we have that nice orange color, and we have 2 of them. And then the blue, we have 2 of the blues. And then we have that black, so there's the black. The black there would be 2. Then the others, I only have 1 white, and I have 1 magenta, and I have 1 green, right? And you can see there 2 plus 2 plus 2 plus 2, 1 plus 1 plus 1 plus 1 gives me my total there. So here we just have 11 objects, but we have a number of those objects that are identical. Now let's look at the solution. There we have our 11 files, and we know this is the data that we have, which ones are duplicated. Now, if we have 11 files and they were all identical, no duplicates, then those 11 files could then be arranged in 11 factorial ways. Okay. Then the number of different arrangements we can get now, because we have to compensate for those that are identical, we have to take there's the 11 factorial, but there'll be, because of the duplicates, we have 2 yellows, so we'll have to divide that by 2 factorial, and then we have 2 blue that we have to divide by 2 factorial, and then we also have to divide it by 2 factorial for the orange and 2 factorial for the black, right? And if you compute that, you can see it gives us quite a large number, 2,494,800 options. So let's just see what we've done there. 11, so it would be 11 factorial. We have to compensate for the duplicates. There are 2 yellows, so I have to divide everything by 2 factorial, and then I times it by 2 factorial for the blue, and times by 2 factorial, and times. They're all in the denominator. Now let's formulate a general rule for arrangement of objects where some of the objects are identical. So if we have n objects and we've got object R where there's some repetition, and object P there's some repetition, object K where there's some identical, right? There could be more than one K, more than one occurring of that particular object. How can they be arranged? And we then have n factorial, that's the number of objects, and because of R, so we have small r factorial and small p factorial and small k factorial. Let me just explain the lowercase here. The n there is quite clear. N is actually the number of objects that you want to arrange, right? Then this small r is the number of object capital R, right? So capital R, let's say there are 5 of those objects identical, then this will be 5 factorial. And the same there's capital P, and the number of objects of capital P is the lowercase, and the number of object K that are repeated, that's lowercase there. And that is what we now have, right? So that's the number of identical objects R, P is the number of identical objects P, and K is the number of identical objects K, right? So that's our formula, which we have arrangement of objects, and some of the objects are identical, and we compensate by dividing. Now it's your chance again to apply the rule. So let's do an example. Determine how many different ways can the letters of the word Ubuntu be arranged. Just to help you, I did some coloring. You're going to do the counting. So you have to see how many different ways all those letters of Ubuntu can be. So again, pause the video, and I think 1 minute should be sufficient, right? So let's see. Let's pause. Now let's look at your solution. The letter U is repeated 3 times, right? That's the only letter that's repeated. And how many letters are there all together? There are 6 letters. And if they were different, I would have had 6 factorial ways of arranging those 6. But I have to compensate for those letter U that's repeated. So therefore it will be 6 factorial divided by, that's correct, by 3, because there are 3 U's, by 3 factorial, right? And if I calculate that, and there we have the answer, 120. Very good. Example for you to try. In how many different ways can all the letters of the word constitution be arranged? I've helped you there with a little bit of coloring there. So I suggest you pause the video, and 2 minutes at most, and then you check your solution. So let's pause here. Now let's look at the solution. As you can see, there are 4 of the letters that are repeated. As you can see there's the T, there are 3 of them, there are 2 I's, there are 2 O's and 2 N's, and the letters C, S, and U are not repeated. There are 12 letters altogether. So if they were all different, we could arrange them in 12 factorial ways. Very good, 12 factorial ways. But we have to compensate for those letters that are repeated, right? So we have to compensate for that. So first of all, we have the 12 factorial, but we have to compensate for the repetitions. There's 3 T's, so that will have to be 3 factorial. We have 2 I's, so that's 2 factorial, 2 O's, that's 2 factorial, 2 N's, and that is 2 factorial. And let's calculate that. And there we have the answer. Quite a large answer, 9,979,200, right? So we have 12, the 3 T's, so we divide by 3, because we're compensating for, you know, those 3 T's. Remember we had the one with the 2 R's. We could have, we'll get a lot of identical ones there. So we have to compensate by dividing by 3 factorial, 2 factorial, 2 factorial, and 2 factorial. Next, we're going to look at arrangement of different objects, but with repetition of objects being allowed. So let's take an example, and with this, looking at these examples there, we'll be able to determine a general rule that can be applied for answering this type of question here. So determine how many arrangements of 4 of the 6 flower stems in a row, there's a 6 flower stems in a row, that is possible if repetition of flowers is allowed. So we wanted to have 4 flowers to be placed in a vase, and they must be placed in a row like that. So that's just for you to understand. So let's see what we have here. First of all, we have 4 flowers. So we have, first of all, we choose the first one, and then the next one, and the third one, and the fourth one. So how many flowers do we have available? That's correct, we have 6. So I can choose any of the 6, right? Then next, they say repetition is allowed. So in other words, for the second vase, I can put any of those 6 flowers in again. And the same with the third vase, I can put any of the 6 flowers in there as well, right? And for the fourth one, I can have any of the 6. So we actually have 6 times 6 times 6. But what it means here, I can have a tulip here, and then the same, another tulip, and another tulip, and another tulip. I can have 4 identical flowers that I can have there, right? Or I can have a rose and a rose and a rose and a rose. Or I can even have the option here, I have an iris and a rose and a rose. So you can have, so repetition is allowed here. And when you have repetition here, your number of choices actually increase. You have 6 times 6 times 6, which is actually 6, and it's 4, so it's 6 to the 4. And if we calculate that, that's 1,296 options there, if repetition is allowed. Now from the example, we can see that arrangement of different objects, if repetition of objects is allowed, we can actually form a very simple general rule. If R of n different objects can be arranged into the exponent R different ways, if repetition is allowed, right? It's into the exponent R. So we actually get a power here. Now let's give you an example. Determine using the 5 color bulbs how many arrangements of 6 light bulbs in a row is possible if repetition of colors is allowed. There's 5 bulbs, and we want to have a row of 6 bulbs there. So again, this is the example for you to try. Pause the video, and 1 minute should be more than enough, and then we come back and then you start it again. So let's do that. So let's pause. Okay, let's start and see what you had there. So the first one is you can have a bulb 1, a bulb 2, bulb 3, bulb 4, bulb 5, bulb 6, right? Because repetition is allowed, I have 5, so I can have any of the 5 bulbs there. And for the second one, I can have any of the 5, any of the 5, any of the 5, any of the 5, any of the 5. So there are 6, so the actual number of arrangements I can have there will be 5 to the exponent 6. And 5 to the exponent 6 is 15,625. Okay. So I can have a red, 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 or I can have red, red, and I can have blue, blue, and I can have green, green. So you see there can be repetition of colors. And so there's quite a lot of possible arrangements there. So now we're next going to look at counting seating arrangements. Let us consider the first example of seating arrangements here. So we see there we have 3 boys and 2 girls that need to be seated in a row, and there are some questions. We've got there's no restrictions, and we have genders must sit together, and then boys must sit together. So there's the group, 3 boys and 2 girls, and they obviously have to sit, if they're 5, they have to sit in 5 chairs, and the chairs are in a row. So we're going to look at the solution of this problem here. Let's consider the first one. You can also pause that, and you can try to do the solution on your own, and then later you can continue. So 3 boys and 2 girls have to be seated in a row. There's the seats there. So let's just call them boy 1, boy 2, boy 3, and girl 1 and girl 2. the first one, they say there's no restrictions how they sit. So let's see now. So we actually need a total of 5 people that need to be seated. And let's look at the seating arrangement. How can we arrange 5 different things? And all of them, that's 5 factorial. So the first one is quite simple using our rules that we developed previously. Now we have a question here. The 2 genders must sit together. In other words, the boys must sit with the boys and the girls must sit with the girls. So let's see what we have here. So the restriction here is the genders must be together, and that's a positive restriction there. So there's the so let's keep the boys together. So there's the boys. Let's put them together in a group, and then the girls must be together in a group there, right? So we can have the boys, 3 boys in the first 3 seats, and the girls in the other 2. Then we can have the 2 girls in the first 2 seats and the boys in the last 3. Or we can have the, and we can continue there. So it's actually the boys and the girls. So there's 2 genders that we need to arrange there. So let's see now. How many genders are there? There are 2, so we can either have boys and girls, or we can have girls and boys. So there are 2 ways of doing that. And how many boys are there? We have 3 boys. So the boys can be arranged. You can have different arrangement of those 3 boys. So that's 3 factorial. And how many girls are there? There are 2, so they can be arranged there. So the total number of arrangement, if the girls must and the boys must sit together, would be 2 factorial times 3 factorial times 2 factorial, which is 24. Let's look at the example again and look at the third question. The boys must sit together. There's the 3 boys and the 3 girls. So there's a restriction here with the seating arrangement, and this is a positive restriction. The boys must sit together. So the 3 boys must sit together. How can they sit together? They can occupy the first 3 seats, or they can occupy the middle 3 seats, or they can occupy the last 3 seats. That's the only way they can sit together. So if we look at where the girls must sit, the girls can then have to fill the vacant seats there. So it's the 2 seats at the back, or the 2 seats at the end, or the 2 seats in front. Now, if we look at actually how many objects need to be arranged there, it's the group of boys, which is 1, the 1 girl and the other. So there's 3 objects or 3 entities that need to be arranged, right? So that's the 3 entities. Then also the boys need to be arranged. So after I arrange the entities, I must arrange the group of 3 boys. So how many entities are there? 3, so that's 3 factorial. How many boys are there? 3 factorial, right? So if the boys must sit together, then we have the number of seating arrangements there is 3 factorial times 3 factorial, which is equal to 36. Now let's look at the 4th situation here of the 3 boys and 2 girls. They have to sit in a row of 5. But let's see what the question is here. The boys and girls must sit alternately. What does that mean? The only way they can sit alternately is there are more boys. So we'll have to have a boy and a girl and a boy and a girl and a boy, right? That's the only way they can sit. So the option for these 5 here would be boy, 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 right? And then the girls must sit in between them. That's the only way we can have them sitting alternately. So let's look at this. So I mean, those 3 boys, they just have to be, they can be arranged in, 3 boys need to be arranged, and then the 2 girls need to be arranged. We'll show you the number of arrangements now. So they're actually 2 entities. So it's just arranging the 3 boys and arranging the 3 girls. Sitting alternately, there's only one way they can sit alternately, and that is the way there. There's only one way they can sit. How many boys do we have? 3. So the boys can be arranged in 3 factorial ways, and the girls can be arranged in 2 factorial ways. So sitting alternately, they have to sit 1 times 3 factorial times 2 factorial, and if we calculate that, that's exactly 12. Let's look at one more situation of the 3 boys and 2 girls that need to be seated. So in this case here, it says the youngest boy and girl must sit together. Okay, so let's assume that the youngest boy is boy 1 and the youngest girl is girl 1, right? Just decide the two of them, they're the youngest one, so they must be together, and there's no restriction on the others. So so there are 3 other, so it's still 2 more boys that need to be seated and 1 girl, right? So if we now look at how many objects need to be arranged, it's the youngest pair and then those 3 other individuals there. So it's 1, 2, 3, 4. So we actually have 4 objects that need to be arranged. How many ways can 4 objects be arranged? All of them must be, then it will be 4 factorial. The youngest pair, remember I can have boy, girl, or they can sit girl, pair can be arranged in 2 factorial ways. So the number of seating arrangements, if the youngest boy and girl must sit together, is 4 factorial times 2 factorial, and if we calculate that, that's exactly 48. Let's look at one more situation of the seating of the 3 boys and 2 girls. This one here, one of the boys does not want to sit in the middle seat. Okay, so let's look at this here. So here we have a negative restriction. Let's say it's boy 1. So when we have a negative restriction, let's do the opposite there. Consider the case where boy 1 sits in the middle, right? Although they said not, let's look at the case where he sits in the middle. So if boy 1 sits in the middle, that's the only place he can sit, right in the middle. That means the other learners, how many of them are still there? 4. So they need to be arranged, right? But if they have to be, so you can have, so it's the boys, the 2 other boys, and it's the 2 other girls there. Okay, so let's just see what we have here. So those 4 people, there's 4, it's the 2 boys and the 2 girls, they need to be arranged there. Well, this is fixed. So how many ways can 4 objects be arranged? That's correct. It can be in 4 factorial. But this boy, there's only one place it can sit. So there's only one option for the boy sitting in the middle. And if we calculate that, it will be 4 factorial. Now, because we have a negation, let's look at the number of unrestricted seating arrangements. How many people are there? There are 5. So 5 factorial. So 5 people can sit in be arranged in 5 factorial ways. Now let's come to our question. If we want to find out the case where the boy does not want to, this is the number of cases where he sits in the middle. And if he not sits in the middle, it will be the difference between the unrestricted seating minus the case where he sits in the middle, and that is 120. If we work out 4 factorial, it's 120. 5 factorial is 120, and 4 factorial is 24. And if we subtract that, there are 96 ways in which one of the boys will not sit in the middle seat, right? Let's just go over this again. See, there we have a negation. So we say does not want to sit, so we consider the case where the person is sitting. And then we can see there's 4 that must be arranged, so that's a 4 there, right? And then once we have that, we just find the unrestricted seating arrangement. And that's just how can 5 of them sit. And then we find the difference between the 2. And that will be the number of seating arrangements, where in this case, the boy will not sit in the middle seat. Now we come to the most important part, the exercise worksheet, right? Before you start the exercise worksheet, I always advise that you go through these examples again. You know, look at the example, pause it, and then try to do it on your own, and then you can check, right? So go through them first. Don't just start with the exercise. And the examples I've taken from the exercise, I've actually taken it from external question papers, Department of Basic Education. And exactly, maybe just here and there I maybe adapted it slightly. So we'll just quickly look at that. This example here, actually look at some counting arrangements. And in this one here, we also have arrangements of objects in this question. And this last one here, we also have arrangements of boys and girls, so this will be applicable to what we've done in this part 1. Thank you very much for viewing this video, which was part 1 of the fundamental counting principle. We suggest that you also view part 2 of the fundamental counting principle, as well as other videos that's been created on grade 12 CAPS mathematics topics. Please subscribe to our channel, Govan Mbeki Mathematics Development Centre, Nelson Mandela University. Thank you very much.